Hello, everybody. Good afternoon. Thank you for joining us today. This is Building and Optimizing Data Lake on Amazon S3. My name is Oleg. I'm an engineer with Amazon S3. I'm joined by my colleague Huey, who's a product manager in Amazon S3. And we're both very excited about this, as I'm sure you are as well. Later, we're going to be joined by Ryan Blue, who is a co-creator of Apache Iceberg, an open table format which has been gaining an incredibly rapid uptake in the data lake ecosystem. So stick around. We have a lot of interesting content for you today. Now, when we talk about data lakes, different images comes up in different people's mind. You may be thinking about big data analytics. You may be thinking about AI, ML, generative AI, perhaps backup restore, pictures of cats. Now, all of these things can be stored in your data lake. So the general space of data lake is incredibly broad. And if we try to just focus on the things that AWS has implemented and supported in the space of data lake, we'll be here a very long time. So we're not going to do that. We're not going to try to boil the ocean or the lake. That's where the last dead joke today. Instead, we're going to look at what underpins every single data lake, its storage layer. Every data lake needs one. Without storage layer, there is no data. Without data, there is no workload. Without workload, well, there's no point. And so today, we're going to dig deeper into Amazon S3 and why we believe it's a great foundation for building and running and optimizing data lakes. And there is one word you will find us using a lot today, and that is scale. And some of you know, and we will reinforce, scale plays an incredibly important role in data lake ecosystem and actually a huge role in the decisions we made in Amazon S3 architecture. So before we go digging deep into Amazon S3, I'd like us to take a very quick trip down memory lane into data lake history. Don't worry, we're not going to spend a lot of time there, just enough to capture one moment in data lake evolution and see a curious pattern that keeps repeating. Now, the term data lake was coined 2010, 2011 probably, but the very thing it describes, which is a repository of structured and unstructured data, has existed for a while, and much, much longer than this. And to pinpoint a time when they first appear is very hard, but we can go as far as the 90s, perhaps, where sort of a client-server architecture was the revolutionary development. And so in a typical business, in a typical IT, you will have a system that looks something like this. You will have a relational database, you will have your email server, file share, and all of this would be placed on the intranet, which was the height of sophistication of technology, and it worked really great. There is two things that are interesting here. First of all, this kind of begins to resemble a data lake. You have your structured and unstructured data placed together. But another aspect here is that it's not placed exactly together. It's placed close to each other, but there is actually areas of data that are disparate from one another. And this is sometimes something we describe as data silos. Now, in the 90s, in this particular configuration, it probably made very little difference. But as things evolve, it actually makes a lot of difference. Now, as your business is growing, it's presumably growing across all dimensions. So your data set is growing, your user base is growing, and the kind of things you do, your scenarios, are exploding as well. And so we need to scale. And to scale, you need to add machines. And in the 90s, this is literally what you did. And so you may have started somewhere here, but then over time, you may have ended somewhere in the system that looks something like this. And the sheer scale of this and the sheer awkwardness of trying to imagine running a report across all of these databases, so joining this data with your invoices on your file server, is incredibly difficult. Imagine trying to secure this with some kind of a coherent governance policy. It's really, really hard. And the primary reason for this are those cylinders again, the silos. It's a very disparate systems, and they're really beginning to bite. So what did the industry do at the time? It invented what it called data marts, which actually pushed all of the data together again into what some of the systems at the time called multidimensional cube. And so this automatically solved some of the problems we just outlined through innovation. Now, the story doesn't end here, of course, but we're not going to go into the rest of it. And much more happens down the road. But let's look at what we just saw. We saw the cycle of breakdown or cycle of innovation, depending on how you look at it. I prefer to look at a cycle of innovation. You start with a certain system that fits your needs. You move your data to it. And as you ingest more and more data into it, and as your scenarios evolving at the same time, the system starts stretching until it eventually breaks down. And in order for you to move forward, you have to innovate. And the two vectors that move this cycle is the business needs that keep evolving over time and the scale, the physical growth of data, personas, and scenarios. And of course, this is all happening today. 20 years ago, we didn't worry about data locality, for example. Now it seems like it's all we worry about. And this is not going to stop. This is going to continue going faster and faster and faster. And of course, we can all continue working in this space. We're all technical workers, and we can rebuild our systems. But if that's all we do, then we don't get to focus on our business. And which is why you want something like this. And of course, this is an Amazon conference. I'm going to talk to you about Amazon S3. But I'm not going to go and recite all of the features of Amazon S3 and all of the scenarios and support, of which there are many. I hope that you visit other sessions that will go really deep into the governance and the cost-saving model and the best practices and the conversations around scale and Amazon S3 architecture. But one of the things that I would really like to double down right now is to talk to you about scale. And this is what's particularly pertinent to our conversation. Amazon S3 is not only built for scale, in fact, somehow paradoxically, it thrives at scale. It relies on scale to support certain scenarios. And we'll get into specific examples of what that looks like and why you should care. So let's look at just some of the mechanisms for how we achieve this. And let's start pretty simple. And as we probably realize very quickly, it's going to get really complicated really quickly. Let's look at a put. So when customer puts an object into Amazon S3, the first thing we do is we shard it. We basically split it into multiple chunks. We also create additional parity chunks. This process is called erasure coding. And then we store it on hard drives. But we don't just dump it all together. We spread it across the variety of hard drives, across multiple racks, multiple AZs, and a variety of facilities. And on get, you would reconstruct this objects back. And so this particular design has two very important implications. First of all, individual customer data only occupies a tiny amount of an individual drive. And so if something happens to this drive, as we know hardware fails, you haven't lost the entire object. In fact, you have enough shard to restore it. So it's great for durability posture. The flip side of this benefit is that the customer data is spread across multiple facilities and disk, which allows you to actually exercise huge parallelism of different resources in order to serve your requests. And this is actually incredibly important for performance. And let's see why. Consider two data lake workloads. Maybe a little bit contrived, but they should drive the point home. The first one operates on a relatively small data set, 4 petabytes. It's not that huge. It's relatively large, but it's not that huge. But what is interesting about it is that the workload being driven is incredibly spiky. We're looking at millions of TPS. Maybe it's a quarterly report or yearly reports or very large ETL that is running. Consider another workload. We have a much bigger data set, several times bigger. But the TPS is actually much lower. We're talking about thousands of TPS over millions of TPS. If you compare these two workloads and try to design a storage system that accommodates both, with performance and durability and availability characteristics that scale, it's actually very hard. They're very, very different. But turns out that scale actually helps. Scale is a challenge, but it's also an opportunity. And opportunity is to aggregate hundreds of thousands of workloads into one aggregate demand. What you're seeing on the left is a set of workloads with very different shapes. And on the right, the aggregate demand. And as you can see, even though each workload is very much a snowflake of its own, and it has very different fingerprint and very different shape and TPS and IOPS demand, the aggregate demand is actually fairly flat. And that kind of system is much easier to build. So this is a great example of how Amazon S3 actually relies on scale to support performance and availability as we do. Scale is truly at the core of everything that we do. To give you an idea of our scale, I'm not going to recite all of this, just two stats that still boggle my mind. Worldwide, Amazon S3 stores 1/3 quadrillion of objects. I don't think my brain is designed yet to hold the number that big. And at peak, we serve 1 petabyte a second of traffic, which is also a crazy number. But the number that impressed me the most, and I just learned about it recently, is that some customers have buckets that spread across million drives or more. And this is the storage disaggregation that we've been talking about. OK, so why does it matter? Turns out there are some very tangible implications of this. And performance is where you can really experience this. So let's start with basics. Each operation against Amazon S3 is a request. And then there is a response. And workload is made of series of these requests. And sometimes you have options around issuing them serially or issuing them in parallel. And data lakes typically drive workloads that issue a lot of requests in parallel because, well, multiple workers, and it's the primary scaling mechanism, one of the advantages of why data lake workloads can process so much data. But if you consider what kind of a capability storage system needs to support to be able to handle this, it's actually very specific. If you drive a million IOPS against your local hard drive, it will melt down. You will not increase your performance. In fact, you will arrive at a congestive collapse. And some storage systems will behave this way. But S3 is not like this because of all the correlation we're talking about. In fact, you can and should send as many requests to S3 as you can in parallel. In fact, really, as many as you can. Buckets in S3, general purpose, are not actually scaling units. And so your TPS, and we'll talk a little bit about the namespace TPS and some constraints it's introduced, is generally speaking can scale up to really, really high numbers. So what it means for data lakes, do use parallelism, do use many workloads. There is more scaling dimensions. Again, let's go back to the basics. Let's consider a put request, but let's consider it in slow motion. So when a request is made against S3, what really happens is the client, well, there's a lot of things that happen, but what client does, first of all, it needs to find a host to talk to. And what it does, it has an endpoint DNS, which is registered in domain name service, and it queries it, and it gets back an IP address. And then it sends a request to this IP address. Typically, it's a load balancer. And so here you have a customer interacting with a single load balancer. And so all of the requests from this customer are going to continue going to this load balancer. In fact, whatever the IP address this DNS resolved to will be sent to this load balancer. Load balancers scale very well, but they're still a singular thing. So there is actually an opportunity to scale it across multiple dimensions, and DNS is the way we can allow this. And it's not a trivial thought that comes to mind, but it's actually a very simple idea. So starting this year, S3 relies on what is called multi-value answer routing. And the principle is really simple. Based on a single DNS name, multiple IP addresses are getting returned. One of them is considered primary, but there is a secondary address you can also send your request to. And so now you get a list of this load balancer. And so if you send your requests and parallelize them across many of them, you can parallelize across endpoints. OK, so we looked at parallelizing operations and parallelizing endpoints. And all of this, again, speaks to the scale, and all of this is enabled by the way Amazon S3 is built. Now, we talked about two parallelization dimensions. What about individual operations? Data lakes actually typically work with pretty chunky objects. Megabytes, 10, hundreds megabytes, gigabytes. And if you try to upload or download an object on a single request, well, it's going to take you some time, obviously. And so performance-wise, it's subpar. Also, if you have any error that happens during the time, you're going to have to retry the whole thing. So can you parallelize within a single operation? The answer is yes. Amazon S3 supports what is called multi-part uploads, which allows you to upload objects in chunks. And because, again, of the correlation of storage and parallelization across, well, all dimensions, generally speaking, the performance of individual upload is completely independent from performance of other uploads. And so if you have more uploads, you get more throughput. You get better performance. The flip side of it exists on the downloads as well through what we call ranged gets. You don't have to fetch an entire object from Amazon S3. You can fetch a range of bytes that you specify. And exactly the same principle apply. If you chop up your object into chunks and download them as parallel, most of the time, the kind of performance you get from this process will allow you to end time your throughput and thus dramatically decrease the performance. I mean, dramatically improve the performance or dramatically decrease the time it takes for your workload to run. OK. So these are scaling dimensions that pertain to basically bytes and requests. There is another interesting scaling dimension in S3 which interacts with them in interesting ways, and that is the namespace of S3. Now, those of you who are familiar with HDFS some may think of S3 as more of a file system. It isn't. It was designed as a blob store. Sure, keys can have forward slashes, but S3, for all intents and purposes, ignores those. And so S3 doesn't scale based on directories. It scales on what we call prefixes. Prefixes is similar to directories, but they basically constitute the beginning of your key. And so the entire key space of an entire region is chopped up in these individual scaling blocks that we call prefixes. And each prefix has these dimensions: 5,500 TPS on read, 3,500 TPS on write. Obviously, this is not enough because the traffic constantly fluctuates across the region. And so Amazon S3 has a scaling machinery that runs in the background that consistently observes this TPS and scales the backend based on that. And so new prefixes are getting built, which increase the overall TPS. Let's consider an example to see what sort of a behavior it can introduce and maybe ways in which we can optimize it. Now, those of you who have come to re:Invent before probably have heard this example. It's just so good, we keep repeating it. Let's consider autonomous vehicles. You have a garage, you have a bunch of autonomous vehicles sitting there. Every morning, they drive out into the world, and then in the evening, they come back, and then they upload all of the data that they have collected. And so you have a bucket, and you have some kind of a pattern of keys that is being used to upload the data. This organization is fairly sensible, particularly for humans. You have some kind of a root directory, you have a date, you have a car ID, and finally, you have your data. What you see here is that a lot of these keys, and that is underlined in white, actually have exactly the same characters in the beginning of it, which means they're most likely going to end up in the same S3 namespace scaling prefix. And so your good put, which is the throughput of request that succeeds, or TPS of request that succeeds in this case, may look something like this. Your TPS, as your car is uploading the data, the TPS is growing, then there is the moment of plateau, and this is probably because we have just hit the scaling limit of individual S3 namespace prefix. And as the time goes by, you may receive some pushback from S3 in the form of 503 errors, which basically tell you to retry. And again, most of the time, you just do that. You have this plateau happening, and then it spikes back up again because the S3 has scaled everything in the backend. So this is what you would sometimes see. And sometimes you may be completely fine with it. In fact, for a lot of workloads, it's completely reasonable. However, there is a way sometimes to do better, particularly given that data lakes commonly drive very spiky workloads when TPS goes up like this. And so one of the options that we recommend is to introduce what we call entropy. And entropy is basically a sorting or hashing mechanism by which you insert which are seemingly random characters close to the start of the prefix. But they're really typically a hash of the rest of the key, for example, a hash of something anyway that is deterministic. But what this results in is that the common prefix of these keys is shrunk now to a relatively small number of characters, and that means that these things, likely these keys, are going to end up in different scaling prefixes in S3. And that means that instead of hitting one prefix with your TPS, you're hitting many at the same time, which means you can support much higher TPS. So this is another example of the very different scaling mechanic that S3 has selected for its namespace. And let's discuss how we can actually apply these things when it comes to data lakes. Object size. This is an interesting conversation because there is a healthy tension that exists between the scaling of namespace and scaling of the byte upload, for example. Because we want to parallelize as much uploads as possible. That means higher TPS on your key space. Or you can reduce your TPS on key space, but then you have larger objects and thus less parallelism. And so we recommend finding a number that works well for your specific workloads. The place to start is sort of a medium chunky objects around 10 megabytes, which typically results in more optimal cost profile and performance profile. But you should definitely experiment based on your specific workload. Object formats are very important for several reasons. Very frequent, we used to use a lot of formats like CSV, TSV, but columnar formats like ORC and to a great extent Parquet have become very, very popular, and there is a very good reason for that. They're incredibly IO-friendly. They're supported by a wide range of analytics products. And because of that, a lot of analytics products are actually optimized for them specifically. So when considering the format of the objects, selecting a well-adopted columnar format such as Parquet is probably a better choice. Table format is something we haven't spoken before. And table format is a concept that basically describes how your objects composed into tables. Traditionally, for the longest period of time, and it came from HDFS itself, Hive used hierarchical format based on the directories. That created a set of problems which we're going to talk about in a little bit later, and Hugh and Ryan will cover how open table formats address this. So selection of the type of a table format is also very important for the performance on your data lake. Now, the previous slide is where we would typically finish when we talk about performance, but today is a special year, and we're going to talk about new offering, which is S3 Express One Zone. It's a new flavor of S3, if you will. It's a new storage class, and it focuses on request-intensive workloads. A lot of what we discussed before about general purpose S3 buckets is that throughput typically is what you care about. But there are workloads where a lot of requests go between the client and the server, and latency, byte to first latency, matters tremendously. And so S3 has undergone through yet another cycle of breakdown and innovation, and we came up with this particular offering. It scales to millions of requests a minute. It actually has a different scaling model for the namespace that we discussed, which I'm going to get to in a second. And it has a very stable performance profile. Let's mention the scaling model a little bit. So the classic general purpose bucket, as we discussed, they don't come with a predefined scaling TPS. In fact, bucket is not a scaling unit in S3 general purpose. But in directory buckets, which is the type of the buckets we introduced with this new offering, actually come pre-scaled. And that makes sense because we focus on workloads with low latency and a lot of requests back and forth. And so to achieve a very low latency, we have to pre-scale these buckets. And so buckets in the system is actually a new scaling unit. And they come pre-scaled with about 100K TPS. And this is another example of S3 innovating in a different dimension. It's not magic, and we can get into the architecture of this, but this is not what this talk is about. The point I want to bring home here is, yet again, S3 relies on this incredible scale to innovate. And in this particular example, we not only did we create an entirely new namespace to support high TPS and low latency, not only we put it into a single AZ to achieve reduced network hops, but we focused on everything that we know how to focus on. For example, we even changed the authentication model to session-based because we know that auth actually adds substantial latency, or made substantial latency to your request. And to give you an idea of the kind of benefit that we see with S3 Express One Zone for analytics workloads, which are request heavy, these are some really, really interesting numbers. There is a lot of sessions on this particular offering. It was mentioned in keynotes. There's a lot more coming up. And if you're interested, please talk to us about it. Now, this is an example of the way we innovated inside Amazon S3 on the back end. We also outlined a lot of best practices around parallelize everything, use this type of auth, and so on. But we've been thinking about what to do to actually make it easier for the customers, how to make these things work in practice. Another area of innovation that we've been engaged in is innovating on the client. And this is not a new product, but this is a product to truly achieve maturity this year. It is AWS Common Runtime, CRT. It is an incredible, you can think about it as a best practices in code. It is a product, parts of it is written in native code for high performance. It utilizes very specific performance characteristics on the individual operating systems. It is now integrated and has been integrated into AWS SDK, and it's currently in the process of being integrated into a wide variety of data lake connectors, such as S3A. We have covered a lot of ground, talking about the 3 scaling dimensions and how they apply to performance. So if there is one lesson to learn here is that our S3 architecture thrives at scale. But performance is not the only aspect for which this is true. And in continuing with this theme, Huey will talk more about other S3 capabilities as it pertains to cost and governance. Thank you.
Hi, everyone. I'm Huey from the S3 product team, and let's now talk about scale. So coming back to our themes about building and operating a S3 data lake at scale, as your data lake scale, you kind of want to put some cost optimization techniques and practices and features in place so that your AWS build, and cost doesn't scale linearly with your data lakes. And so in this section, we're going to talk about some of these features and practices you can put into practice. The first thing is storage classes. This is the bread and butter of S3, and over the years, we built a large number of storage classes, and the idea behind those storage classes is that there's different kind of workloads, analytics and backups and media and entertainment, and each of those workloads have their own specific access pattern. And the idea of these storage classes is that how can we build a sort of a storage tier that on one hand optimize cost for you, but on the other hand doesn't really sacrifice performance. And with that in mind, today there's a large number of storage classes that you can choose depending on the specific access pattern and the specific workloads that you have. So on one hand of the spectrum, and this is very typical for a lot of analytics workloads where the data is frequently accessed, you can use S3 standard. And on the other end of the spectrum, for long-term archive data where you don't quite really need, you have Glacier Deep Archive and sort of everything in between. And as Oleg mentioned, we just launched S3 Express 1 Zone as well for that kind of even lower latencies, higher TPS workloads. But one thing to know about access pattern is that typically it's not static. And this is especially true for analytic and data lake workloads where usually like fresher data, the newly ingested data is more frequently accessed. But then as time goes on, those data tend to get a little bit colder. And what you want to do to put into place is that how you can, some kind of features or something that you can help you transition data from hotter tier, like S3 standard, to colder tier, like Glacier, as the data becomes colder. And with that, we built S3 Lifecycle. And just out of curiosity, how many of you guys have heard of S3 Lifecycle or currently using it? Okay, great. So I don't have to spend too much time on this. So Lifecycle is S3 feature that help you transition storage classes at scale. The way that it works is that you configure rules, specifying what's some of the criteria you want to fulfill in order for the transition to happen. So time-based is one. And then S3 will manage that transition for you. And as with everything, Lifecycle is built with scale in mind. A lot of customers use Lifecycle to delete data in like a large chunk. And you can use Lifecycle to transition or delete data for billions of objects in petabyte scale data lake. Now, with storage classes and Lifecycle, what that also means for you is that you need to be pretty familiar with your access pattern and also pretty familiar with S3's offering to figure out what is my access pattern and what is the best S3 storage class for that access pattern. And that could be a lot of work from your end to do all the research and do all the monitoring access pattern. And you might just want sort of a magic wand S3 storage class or feature that take care of the storage class transition and access pattern monitoring for you. And with that, we have S3 intelligent tiering. Also curious, how many of you guys heard of intelligent tiering or are currently using intelligent tiering? Okay, a little bit less. Interesting, that's less than Lifecycle. So intelligent tiering is this new storage, well not new storage class, the storage class we've launched for a while that basically monitoring the access pattern for you and then transition the data between storage tier without sort of any intervention or work from you. And what that means is that it's really just a S3 and AWS managed way to have automated cost saving. And we're very excited to say that since launch, we've saved customers over $2 billion with intelligent tiering. And that, once again, is using intelligent tiering as like sort of managed, automated way for cost saving without really a lot of work from you. Now, another dimensions, setting aside from the storage classes and Lifecycle, is actually visibility. And we see this a lot with our customer is that if you don't have visibility into how your data is being used, it's very hard to come up with cost optimization things that you need to do. And we're all talking about data lakes here. And one typical path we see a lot of customers run into is that when you first start out building a data lake, it's fairly small scale, maybe a couple dozen data sets, a couple of buckets, a few dozen users. But then you can quickly scale to, let's say, thousands of data sets, hundreds of users, dozens of AWS accounts. And when you get to that scale, you can quickly lose sight of how your data is being used. So how can you get that visibility and try to figure out how your data is being used? The answer is storage lens. I'm gonna ask a lot of questions because I think we all need a little stretching. There's too much sitting this week. How many of you guys have heard of Storage Lens? Okay, perfect. So we launched Storage Lens. It's a feature we launched back in 2020. And the idea there is to give you metrics and visibility into how your data is being used. And one nice thing about Storage Lens is that there's a free tier. So you can go back and start turning it on. And a lot of the metrics are free. And what you can use like Storage Lens for is to ask those kind of questions to help you cost optimize. So a question like, hey, which of my bucket or prefixes are being frequently used? Or am I using the right storage classes for these particular data with this particular access pattern? And with this kind of metrics and what Storage Lens can do for you is that it can start this kind of flywheel of observe, analyze, and optimize. So let's say that you observe that there's a prefix or bucket that's not really frequently used. You start analyzing why that's the case and what kind of workload is causing that. And at that point, you might determine, okay, this data is for long-term archival storage, or I might not need it anymore. Then you can start optimizing using some of the feature we talked about, let's say lifecycle, to either transition a large chunk of data into a colder tier for archival reasons, or you might just delete the data altogether. So a couple takeaways from this section on cost. One is intelligent tiering for automated saving at scale. And I just want to emphasize that that's probably for many of you guys like the most important takeaway is that for most workloads, like if you just pull your data into an intelligent tiering, you just start saving. It's really not a whole lot of work from you, and it can save a lot of money. The second thing is lifecycle, which is if you choose to decide what storage classes and storage tier you want to have control over that, use lifecycle to do that sort of transition. And last but not least is use Storage Lens, especially there's a free tier to start monitoring how your data is being used and use that kind of insight to drive cost optimization actions. So. Let's now talk about security and governance, which is becoming an increasingly hot topic, making sure the right people have the right access to the right data. And coming back to our theme about data governance and to scale is that as your data lake scale, we've seen many customers running into this, is that you have a proliferating number of data sets you want to control access on one hand, and on the other hand, a growing number of user application teams that need access to the data. And that means that data governance and making sure the right people have the right access can become a little bit hairy. And specifically, when we talk to customer about, hey, what kind of S3 data governance challenges you run into, they cite these couple of problems. The first is, as was mentioned, a proliferating number of data sets and users that need access to data. And what customers want is a scalable way to enforce granular S3 access. So you don't want to say that, hey, this user application have access to my entire bucket. You want to say like, hey, this user application can only access this and that data sets. And you want to do that at scale. The second is grant permission directly to identities and external corporate directory. What does that mean? Traditionally, S3 was used for a lot of media entertainment and backup, this kind of workloads, and that means the consumers that's consuming data from S3 are a lot of time applications. But increasingly for analytics and data lake workload, it's not just applications anymore, it's humans. So it's data scientists and data engineer that might want to pull data from S3 into a notebook environment, let's say, run some analysis and start training a machine learning model. And for that, customers want a way to grant S3 access directly to those human, so to speak. And last but not least is auditing. And this is especially important for customer from highly regulated industry like government, financial services, and healthcare, where you want a very detailed view of which user access what data at what time using what application for high volume of S3 access. Now, with all that sort of challenges in mind, the typical way that customers manage access to S3 today is using IAM. And IAM bucket policy. And going through those 3 bullet points, and IAM can be a little bit limiting when it comes to what customer want for data lake access specifically. One, for that proliferating number of users and applications, and you want sort of some way to enforce access at scale, bucket policy usually have a 20 kilobyte size limit, so it's very hard to scale beyond that limit and to enforce that granular access. And second, for that human identity, IAM by nature can only understand IAM principle, so IAM user and roles. And what that means is that customers have to maintain some kind of mapping between their directory user and groups, so AD user, AD group, Okta user, Okta group, into IAM role, and then grant those role access to S3. And that means just more work to provision that roles and maintain that mapping. And last part is auditing. So in a world, which is a very common pattern where Jane and David are in the same AD group and they're sharing this role to access S3, you can't really use CloudTrail to audit which end user access what data, whether it's Jane or whether it's David. You can only see that, okay, this role access the data. And that means that for a customer from highly regulated industries like financial services, government, they will have to build custom solution for that end-to-end auditing to piece together end user access. So with that in mind, sort of the data lake access pattern challenge and the sort of IAM where the gaps can be, we built and recently launched S3 Access Grant to help customer to scale S3 data governance. And very curious, like how many of you guys heard of S3 Access Grant? Okay, sweet. Okay, so we just launched this feature on Sunday, so very exciting. What it allows you to do is that grant S3 access directly to user and groups in your corporate directory. So let's say Azure AD, renamed now as Entra AD, Okta, ping one login, in addition to IAM principle. And you can define access in a very intuitive grant style that's very common in analytics and relational, typical like how you define permission in a relational database, and in a very highly scalable way. So the grants would look like something on the left, where first example here you're granting different access level to different S3 folders to an external AD group. Last example, you're granting different access level to different folders to an IAM role. And in a world of analytics and data lake, you can imagine, first example, you're granting access to a data scientist group. And this data scientists are tasked to pull data from S3 and train the next generation of machine learning model for you guys. And last example is, you can imagine this is for a Spark job, have read access to a staging to ingest like raw logs and then spit out, have write access to the clean folder to spit out the transform tables. And what access grant behind the scene does, and we'll cover this in a bit, is that it vends sort of just-in-time least privileged temporary credential based on the grants. So that just further enhances your security posture because all the credentials is short-term by nature, and you won't have someone have the long-term secret key sitting in their laptop, and as a security guy, you're concerned like someone's gonna hack that. And last but not least, we talked about auditing. So access grant integrate with CloudTrail so that you can use CloudTrail to audit that end user access. So whether it's Jane, whether it's David, even though they're from the same AD group, right, project, whether it's Jane, whether it's David, access the data at what time using what applications. Let's walk through a concrete use case of how you can put access grant in action and just walk through the customer experience. Here is a super high level overview of like a data lake scenario. So you have a data lake in S3 that store a bunch of objects. Could be PDF, JSON, MP4, and you have user that want access. Could be technical user, data scientist, data engineer who can code, or business user who want just an intuitive sort of interface to interact. How do you use access grant to grant access? You have your bucket, and you have your users. The first step to use access grant is that you create a access grant instance. Now, this instance is completely managed by AWS. The concept is just sort of a logical grouping of all the permission and grants that you register. The second step, you register grants, specifying who have what level of access to what S3 resources. And then when user, at time of access, these are, let's say, data scientists, when they want to pull something from a notebook to S3, they will request access via this get data access API, and by calling the access grant instance. And there will be like an endpoint you can call. The access grant instance then will look up all the grants, figure out if the request should be authorized based on the user's identity and based on the grants that you have. if the request is authorized, it will then back temporary credentials. And these temporary credentials, if you guys probably like it's STS token, is what you would get back today by calling assume role. And then using that temporary credentials, customer can now, the client or user can access S3 and pull the data from S3 into a notebook environment, for example. Now, one thing we want to note is how AccessGrant and lake formation can work together. And I'm going to ask one more question, like how many of you guys heard of lake formation or using lake formation? Okay, sweet. So lake formation is another AWS services that help you govern access to structure and catalog data. So think like, glue table, for example. And what AccessGrant does is that it can work in conjunction with lake formation, and with the two feature go hand in hand, you can have a comprehensive data governance solution. So specifically, you can use lake formation to control access or to structure, catalog, tabular data, and you grant access based on role, column, cellular level. And then you use access grants to grant access to unstructured, uncatalogued, unstructured or non-tabular data. So for example, images, audios for machine learning models, or raw logs, newly ingested logs that hasn't been transformed into structured data. So those two data governance products together can help you govern data, all kinds of data, whether it's structured, catalog data, or unstructured, uncatalogued data. Now, the last thing I want to mention is that AccessGrant is part of a bigger AWS story. We talked a lot about directory identities, Active Directory, Okta. There's a big investment on the AWS side that we're trying to make multiple AWS services, including S3, to let you be able to authenticate and authorize against identities in your external corporate directory without going through IAM. And with that kind of picture in mind, AWS IAM Identity Center, formerly known as SSO, is going to be that single entry point for you to onboard your workforce identity. So you onboard your Active Directories, Okta, ping to Identity Center once, and thereafter you can define S3 permissions, Redshift permission, lake formation permission against those external directory identities. So to recap this section, IAM works for most S3 use cases a lot of time, static application access pattern. But for data lake access pattern, if you are running into some of the challenges we talked about, whether it's IAM scalability, granting access to human identities, look into S3 access grants as a sort of complement to IAM for specific data lake pattern. And last but not least is that you can leverage access grants together with lake formation to govern both structured and unstructured data. So at this point, we talked a lot about the fundamental pillars of how you want to think about building a data lake. So performance, cost, security, and data governance. And increasingly, on top of those fundamental pillars, we're seeing the rise of transactional data lakes. And what does that mean? So increasingly, going back to the scaling story, data continue to explode, and number of user and application of concurrent user and application continue to increase, and we're seeing demand from customers that want to combine the traditional warehouse-like capabilities, like whether it's high performance, asset transaction, together with the cost effectiveness and elasticity of S3-centric data lakes. And with that sort of customer demand in mind, we're seeing the rise of a lot of open table formats like Iceberg and Delta Lake, which Ryan will dive into Iceberg very shortly. That basically it's becoming the basis of the new lakehouse architecture. And these table formats bring a lot of exciting capability that are traditionally more associated with warehouses, like isolations, high performance analytics, time travel, and to sort of S3-centric data lakes. Without further ado, I will pass it to Ryan, who can do a much better job than me to talk about icebergs.
Thank you. Hi, everyone. It worked. Okay, good. I'm Ryan Blue. I am the co-creator, along with my Tabular.io co-founder, Dan Weeks, co-creator of the Apache Iceberg project. So today I'd like to talk a little bit more from the, I think, database or usage perspective than what these guys have covered so far, the S3 and object store perspective of data lakes in the cloud, built on top of S3. So the story of Apache Iceberg actually starts about 6 years ago, which is crazy. I can't believe we started the project in 2017. It was so long ago. And it started at Netflix, where Dan and I worked at the time. We were trying to build a cohesive data platform, and one of our central tenets was the separation of compute and storage, specifically built on S3. What we were using at the time was a Hadoop-based infrastructure, so we were running a pretty gigantic Yarn cluster, and S3 was the source of truth for all of the data. So we had a ton of different projects, just a lot of different infrastructure that our team needed to pull together. So things like EMR, we had Spark in the mix there, Presto, which was later renamed to Trino, Amazon Redshift at the time. We were exploring tools like Snowflake. We had streaming through Flink, and also we had just our own custom things, like a custom Hive metastore that was allowing us to scale beyond the limits of just a normal Hive metastore. And we had a lot of problems with this. It was like a puzzle that we just could not figure out how to fit together. Nothing really worked well. And we had a ton of problems. So the problems, after we sat down and looked at this, they fell into 3 different buckets. Number 1 was cost and performance. At Netflix scale, we were trying to deliver all of this data, get value out of it, but we had, I think at the time, tens to hundreds of petabytes. How do we manage that and effectively and efficiently access all of that data? It's awesome that we can store it, but if you can't filter through it and select just what you need for your use case, it's effectively dead, and you're just paying for nothing. The second thing was correctness. Hadoop systems were built with this very simple idea of whatever happens to be in a directory listing, that's what's in your table. And the problem with that is if you need to list multiple directories, or if you need to make changes to multiple directories at the same time, you can't do that atomically. There is no transactional mechanism in a normal file system, let alone S3. And it's even worse if you're trying to view S3 as a file system, because it's not built that way. That's not how it scales. And then the third thing was this bucket that was, I think, made worse by cost and performance and correctness issues. It was the ability of our workforce to actually take advantage of data, to be productive as data engineers, to use the data effectively. That was very hard. So if you're waiting way too long for data to arrive, or if you have correctness problems and you don't trust that while someone else was writing to this table, you were actually able to read it correctly and trust your answer, those of course are productivity issues. But I'm also talking about things like adding a column and realizing it duplicates a column that existed 2 years ago. Hey, it turns out we had profile ID 2 years ago in this table, and we just resurrected data from 2 years ago, and it filtered into our analysis, and that's why we had, hey, 2 million profiles, even though it was a brand new feature just released 5 minutes ago. That sort of thing is really disruptive. What we realized was that at the center of all of these was the Hive table format, and how simplistic simplistic it was to try and keep Parquet files in a directory structure and call that a table. And so what we realized was that we needed to basically steal a whole bunch of ideas from the database world and bring them to the Hadoop world. And that's how we got to Iceberg. We asked ourselves this very simple question: what if we just stole a whole bunch of great ideas from the people who have been doing this for 30 years? Turns out that was a very powerful idea. So what we did was we created Iceberg. Now, it's impossible to think about Iceberg right now from that lens, of where we were 6 years ago. So I'm going to give you the perspective from today, looking backwards about what we built. And I think there are two things that actually really stand out about Iceberg. Number one, it's an open standard for tables. It is something that we wanted to be built into Redshift. And I believe Redshift just announced that their support for Iceberg tables is ready to go, right? That announcement, I believe, came out today. The support across the AWS ecosystem is, really amazing. And we wanted to build a standard and a format that could do that. To do that, we needed to open source it. We needed to make sure it was something that a lot of different companies could standardize on and could really invest their time in. So that was one of the core things that we did. The second thing that we did was we, like I said, stole a whole bunch of great ideas from database people. We said everything is going to have SQL behavior. SQL is a declarative language, which allows the infrastructure itself to make decisions and do the right thing. You tell it how you want something to be, and it figures out the best way to do that. And it can improve on that. Next week, it can figure out the best way to do it given the current state of a table. Or maybe we can release a new version of the database, and it gets even better and even faster. So we wanted SQL behavior. And not just because it can get faster and it's declarative, but because we needed the same guarantees for people to be productive. No unpleasant surprises like zombie data columns. No problems when someone else was writing to a table as you're reading it. We needed to fix those issues. We built it for data engineers to be productive and added things like merge and the transactional data lake queries, time travel, hidden partitioning, so you don't have to worry and retrain analysts to be able to query the table in order to take advantage of the work that you've done to prepare the data for them. Things like that. And another thing that I want to highlight, since we're all S3 nerds in this room, is we built a high-performance design for S3 specifically. So our data lake was on S3, and we wanted to take advantage of the best of S3 and also not do things that just don't fit with an object store. So Apache Iceberg is actually the only open table format that is specifically designed to live in an object store. It was never designed for HDFS, although HDFS and the Hadoop ecosystem benefits pretty substantially by reducing the load on the name node. So first of all, we didn't want to use any list operations that hit the index and tax the index unnecessarily. It's really nice to be able to list and see what's there, but it's not an operation that you actually need to do in order to access data correctly. We want to store everything as a tree structure with hard references so that we never need to go and query the state of S3 to find out the state of a table. Number two, we wanted to remove the rename or move semantics that were needed for commits. In an object store, a rename is actually a back-end copy and a delete. So you're really wasting a lot of cycles and time by not having just unique names, by reusing the same names or having these strategies that rename from one place to another to commit. We also knew that S3 is super smart and does things like it remembers if you've asked if an object exists and it says no. Well, that's not great. It turns out that if you're relying on objects existing in a listing and you go ahead of time and ask if it exists, you might get the cached answer, and that's not great. So we took all of these things into account and we designed this tree structure that never needs to use those features that are not really designed, those features of S3 that make it very difficult to achieve those high performance workloads. We also did something, I think, which is really nice. We didn't realize it until later, but by having this tree structure, what we did was we added the ability to add entropy at the start of our prefixes, at the start of a table. So the old model was to keep everything together for listing purposes. Well, if you don't need to list, then you can put entropy way further up in the key space, shard effectively against those back-end prefixes, and really get excellent performance like Oleg was talking about earlier. The last thing I want to mention is that we introduced a new abstraction, which is file I/O, which is just a more seamless abstraction. So rather than trying to treat S3 as a file system, doing extra checks to say, hey, does anything under this prefix exist? Because this may actually be a directory. We got rid of all of that, and we just treat it as an object store. Now, what ended up happening with Iceberg was actually a bit of a happy accident. So I mentioned that we wanted to fix ACID transactions, have database semantics on top of tables in our object store. And what we actually ended up doing was not just making it so that two Spark processes can use the same table at the same time. We ended up accidentally creating what is now thought of as more universal analytic storage. So remember I was talking about having EMR, Trino, Presto, Flink, and other things in our architecture at the time, and nothing really fit together because if Flink was changing a table, Spark is going to get incorrect results. Now that we've fixed that problem, we're tying all of those different systems together. So you can effectively have this broad data platform with all of the tools that you want for different use cases and needs. Spark, Trino, and all of these are available through, AWS products, EMR, Athena, MSK, Redshift, Kinesis. You can actually use these in a unified data architecture, and it's really, really powerful. And that's what I'm very excited about. We had some amazing use cases that, unfortunately, due to time, I'm going to skip through really quickly. At Netflix, the long story short is basically that we had to go for use cases in order to build trust in a new storage system that we could not have done otherwise. So anyone using a Hive table and fairly happy with it, they said, why do I need to be the first mover, right? Why do I need to be the early adopter? So we went to things like our telemetry data. These are second level measurements of every metric you can imagine across the entire Netflix data platform. This was a massive data set, and it used to take us more than a day or just to try and run a query, and then it would inevitably fail. This case actually took 10 minutes just doing the directory listing to find out what files we needed to read for a query, and then it would go into this 24-hour period before failing. In Iceberg, we got that down to 13 minutes of runtime and 10 seconds of planning time, and then we added additional filtering and additional metadata in the format to skip through files more effectively and do file level pruning. We got the whole thing down to 42 seconds. So this is looking at more than a month of one metric stored in a very, very vast telemetry table. We also had an opportunity to replace an Elasticsearch cluster where we were always querying by the same key. And we used Iceberg metadata to provide an index and store all of that in S3. No need for online or runtime systems, and we were able to use a dynamically scaling Presto cluster and basically reduce the cost by several orders of magnitude. So it was really, really cool. Now, I want to be, in my last minute, a little more forward-looking. So we've talked about how Iceberg has unlocked this universal analytic storage. It's actually just the beginning of what you can do. With S3 as this ubiquitous layer for storage, Iceberg provides a table-level interface to that is really powerful. And so what you're seeing is the emergence of essentially S3, but with a table-level interface on top of it provided by Apache Iceberg. That then, with the ubiquitous availability of engines that connect up to Iceberg and can use that data, we're actually building a different type of data architecture, one where your data is all in one place. It's all in S3. It is a table space as large as you want to make it. And everything goes to S3, one central location for that data. So we're done with the days of you load your data into a database and then you pay that database to get access to your data. Now you grant access to that database through S3. And we're building a more modular architecture where all of those engines play in the exact same central data store. Now, all of this has been built on at least one open standard, Iceberg tables. But it's going to change. And I think to continue on this modular path, we're going to see more governance and security features, things like OAuth 2, REST catalogs, so you can interact with metadata as well. So we need a lot more open standards. But it's a very exciting world where all of our databases in the analytics space are becoming more modular. They're becoming interchangeable. You can use Spark to produce data that you consume in Redshift. Those sorts of use cases never quite worked right in the past, and it's really exciting to see where we're heading. So thank you. That is Apache Iceberg, and I appreciate everyone coming and listening to us.